안녕하세요. AB 비스타의 김재철입니다. 식이섬유 또는 논스타치 포리사카라이드는 여러 원료로부터 기인을 하는데 단위동물 배합사료에 필연적으로 포함되는 항영양인자라고 볼 수 있겠습니다. 이러한 요인 때문에 NSP 분해 효소가 한국 단위동물 사료에 거의 필연적으로 포함이 된다고 볼 수 있겠는데요. 오늘은 마이크 베드포드 박사님을 모시고 NSP 효소제가 어떠한 기작으로 작용하는지 최근의 연구 동향을 기본으로 해서 먼저 설명을 드리고, 그 다음에 저희가 평소에 갖고 있던 NSP 효소제에 대한 오해와 진실들을 질의응답을 통해서 규명하는 시간을 갖도록 하겠습니다.
The first mechanism is the viscosity mechanism. This has been described more than 30 years ago and basically involves parts of the cell walls of the cereals that we use in animal feed dissolving in the intestinal tract. They dissolve and form large gels which actually slow down the diffusion of nutrients, substrates and enzymes and effectively delay digestion and absorption of nutrients. What this effectively means is that the diet is poorly digestible and the animal gets less value out of the diet that's being fed. When we feed an enzyme, what it does is breaks down these large, soluble, viscous polysaccharides into smaller and less innocuous products. As a result, viscosity is reduced significantly and diffusion is restored to normal values. This increases digestibility and the performance of the animal is brought back to normal. Viscosity is a big problem for grains such as wheat and barley and triticale, but we really don't see this as being a problem in corn-soy rations, where viscosity plays a very small part of the response that we see when we're using NSPase enzymes. The cell wall mechanism relies on the fact that the cell walls of the cereals we feed our animals are manufactured or made of polysaccharides which cannot be broken down by the enzymes that the animal produces. These polysaccharides include xylan, beta-glucan and cellulose, and the enzymes needed to break these down simply are not produced by pigs or chickens. The idea then is that we supplement the diet with enzymes that can break down cellulose, xylan and beta-glucan, and as a result break these cell walls open and enable the digestive enzymes of the animal to gain access to any cells which have not been broken down in the milling or pelleting process. The problem with this mechanism is that when we look at how much enzyme is needed to break down these cell walls completely, and the time required to break down these cell walls completely, it is in far excess of what we actually feed the animal. So for example, 100 times the concentration of enzyme that we use commercially is needed to break down cell walls in an in vitro setup, and 24 hours is required as well, as opposed to the 1 or 2 hours that is the time that the cell walls are resident in the gut of the animal. As a result, we really don't believe the cell wall mechanism plays much of a role even in a corn-soy diet where viscosity is not an issue either. The cell wall mechanism, therefore, should not be considered as a principal mechanism when looking at the role that NSPases play in animal feed digestibility. And now we come to the third mechanism, the prebiotic mechanism. As a matter of fact, we like to say this is really a signaling mechanism, not a prebiotic mechanism. But what do we mean by this? When you feed an NSPase, it'll break down fiber into smaller fragments and ultimately produce what are called oligosaccharides. These oligosaccharides are not digested by the animal, but can be fermented by bacteria inhabiting in the gut. The oligosaccharides that can be produced depend on the enzyme that you use. A beta-glucanase would produce gluco-oligosaccharides, and a xylanase, xylo-oligosaccharides, and a mannanase, mano-oligosaccharides, and so on and so on. In the work that we've done so far, we believe the most important by far are the xylo-oligosaccharides, and that's why we're focusing on xylanase in this video and why we're focusing on xylanases in our product portfolio. So what do I mean by signaling? Classically, when people talk about prebiotics, they talk about products which are fermented directly into short-chain fatty acids. We believe that whatever enzyme is used in animal feed, we are never producing significant oligosaccharides in quantity to generate the short-chain fatty acids that we see in the small intestine or in the large intestine. The reason is simply that the quantity of ZOS that our xylanase will produce is very small, and the effect that we see in older animals in terms of short-chain fatty acid concentration increases is very large. So this is what we mean by signaling. Effectively, what we believe is happening is that the ZOS, or the oligosaccharides that the xylanase is generating from the feed, are being picked up by bacteria that can themselves produce xylanase. And these ZOS are being used, if you like, as signals to tell these bacteria to develop, to grow, and to produce their own xylanases in very large quantities. Eventually, and over a long period of time, these bacteria begin to dominate. Xylanase production in the large intestine of the pig and the chicken starts to increase dramatically, and we see far more efficient digestion of fiber as a result. This is one of the mechanisms by which we believe that the prebiotic effect or the signaling effect takes hold. By increasing the microbiome's ability to digest xylan, effectively what we're doing is increasing the concentration of the short-chain fatty acids effectively in the ceca and in the colon of the pig. This has a knock-on effect. Some of the short-chain fatty acids that are produced as a result of these xylanase-produced signals, butyrate in particular, start a cascade of responses where endocrine products are produced in the large intestine, feed back to the stomach, and enable the pig or the chicken to hold on to feed much longer in that part of the digestive tract. So effectively what we're saying is the xylanase is changing the microbiome, changing the concentrations of short-chain fatty acids in the large intestine, and these short-chain fatty acids are feeding back to the stomach and telling the stomach to slow down and don't release feed into the small intestine. This results in a significant improvement in protein digestion. So let's recap the three mechanisms that I've just described. The first one, viscosity. It's not really relevant for corn-soy diets, which is the majority of the diets that you'll see here in Asia. It may be relevant if you're thinking of using wheat or barley. The second mechanism, the cell wall mechanism, for the reasons I described earlier, we really don't believe is a valid mechanism for the use of any kind of NSPAs, whether it's a complex enzyme or a simple xylanase. The third mechanism, the prebiotic mechanism, which we're now calling a signaling mechanism, again for the reasons we described, is a mechanism which we think dominates, particularly in corn-soy diets where the viscosity mechanism just does not apply. This signaling mechanism is of value because it tells you that an enzyme which can produce the xylo-oligosaccharides, and it is xylo-oligosaccharides we're looking for, will eventually improve the ability of the microbiome to digest the most undigested fiber in your diet, and that is the arabinoxylan fraction. This gives far greater benefits in terms of energy and signaling back to the stomach or the gizzard, as described previously. As a result, we believe that feeding the right xylanase that can produce the right signals will give you the best response in commercial feed today.
Thank you, Mike, for explaining all the mechanisms. Now we are going to have some Q&A session to clarify some of the misunderstanding in the market. So the first question I want to ask Mike is, considering the large number of different substrates available in diet in Asia Pacific, what type of fiber degrading enzyme is the most suitable to use?
That's a very good question. I think a lot of people tend to think because the fibers that are being used or the structure of the ingredients that are being used in Asia Pacific are multitudinal. In other words, there's beta-glucan, there's xylan, there's mannan, there's all sorts of other fiber structures in these ingredients. They tend to think that enzymes with activities which address all of those polysaccharides is needed. But as I described earlier, actually what we're really trying to do is train the microbiome to digest the most indigestible portion of your diet. And in virtually every single case, that is xylan. And therefore, what you need to do is generate these oligosaccharides using a xylanase. So a xylanase is actually the most appropriate enzyme to use, even in complex diets.
Okay. The second question that I can ask is, I think the most widespread and compelling industry belief is that the more enzyme activity that you have in the fiber degrading enzyme, the better performance of the enzyme. What is your thought about this belief?
It relates back to the answer I've just given you earlier, and that's actually, a multi-enzyme doesn't give you any extra benefits. As I said, the most indigestible fraction is the xylan, and it's that fraction we want to encourage to be digested. When you look at a multi-enzyme, some of the problems you can get with a multi-enzyme is some of the activities may be detrimental. For example, some multi-enzymes, in fact a lot of multi-enzymes, will have enzymes which break down oligosaccharides. And that's exactly what you do not want to do in a corn-soy diet. We want to create xylo-oligosaccharides as our signaling molecules. Some of these multi-enzymes have xylosidases in them, which break those molecules down to xylose, which is totally ineffective, and in fact, in some cases, can be detrimental.
Okay, that's very good. And the third question I would ask is, it is very widely believed by local nutritionists, especially in Asia Pacific, that xylanase is needed only for wheat-based diet, and the response to xylanase in a corn-soy-based diet is negligible. So what is your thought based on your many years of R&D experience about this concept or this belief?
Xylanases are effective in both corn soy and in wheat soy diets, but actually what we found in recent years is we can make, and this is part of the product that we're introducing into the Korean country, is the product Cygnus has in its own structure added oligosaccharides. Now why do we do this? Xylanases work by, as I've said, making these signaling molecules. Sometimes, on some samples of corn, we don't make very much. And we can supplement that by adding arabinoxylan oligosaccharides to this product. In other words, creating, if you like, an insurance policy. As a result, this product is going to be far more effective and much more consistent than any NSP enzyme that is out there.
Right. Then my fourth question is, I think another method that nutritionists can find challenging is how they can differentiate between many different fiber degrading enzymes in the market, and how they can choose the most effective and economical one. So what are the important characteristics a nutritionist should look at when they are evaluating fiber degrading enzyme?
Yeah, this is a really good question. It's something we get asked all the time. Unfortunately, when you consider now what we know about how these enzymes are working in the animal, they're breaking down the xylan structure of corn and wheat and producing these signaling molecules, that's actually what we want these enzymes to do. It's very difficult to replicate that in vitro. In fact, we haven't been able to up to this point in time. So when you talk about evaluating enzymes in vitro, I would say there is no test that you can use at the moment. The only real test is to actually try them in the field, use them commercially, and have a look at the responses that you see. And one caveat with that, it's no good just simply doing one trial. If you actually look at the xylanase literature and the NSPase literature, you'll notice that you need about 10 or 20 trials before you've got an idea of whether this enzyme is going to be consistent in your environment. We've conducted multiple trials, and if you like, we have de-risked this for you. So I would say do not rely on in vitro tests. Use in vivo tests, use tests under your commercial environment. And if your supplier of your enzyme does not have any tests which mimic the environment into which you're using your enzyme, then I'd be very skeptical that it's going to bring any result in your commercial operation.
Okay, it's very good. I only have one more question. This is my last question. What is the emerging area of enzyme R&D that can possibly be commercialized in the future?
Well, as I said, we have a product we're moving out now called Cygnus, which is an enzyme which is, if you like, reinforced by added oligosaccharides or xylo-oligosaccharides. This is a real advance on the enzymes that are out there, whether they be simple xylanases or NSPases, because it gives greater consistency to the response that we see. Going forward, we're looking at what kinds of oligosaccharides are needed in more detail. So, for example, how long do they have to be? Do they have to be substituted with ribose? But that's for the future, and that's where our research is going.
Thank you, Dr. Mike Bedford. 모쪼록 이 비디오 클립이 NSP 효소제의 작용 기전을 이해하는 계기가 되었길 바랍니다. 또한 NSP 효소제 선택 시 중요하게 고려되어야 할 사항에 대한 전반적인 이해에 도움이 되었길 바랍니다. 감사합니다.